Hello, today we're going to dive into a powerful concept in mathematics, using matrices to represent linear transformations. We'll be focusing on how matrices act like functions that can stretch, rotate, and move shapes in a coordinate plane. Our main goals are to understand how to associate a matrix with a transformation, what the determinant tells us about that transformation, and how we can combine and reverse these transformations using matrix multiplication. Let's start with our first objective. By the end of this scene, you will be able to determine the matrix associated with a linear transformation. Our goal is to understand how any linear transformation can be uniquely represented by a 2 by 2 matrix. First, what is a linear transformation? Simply put, it's a function that maps a vector from a two-dimensional space, which we call R2, to another vector in R2. If we call our transformation L, it takes a vector v and transforms it into a new vector, which we write as L of v. Think of it as taking an input vector and producing an output vector. A key property is that it preserves vector addition and scalar multiplication. This means L of the sum of two vectors is the sum of their transformations, and L of a scalar times a vector is the scalar times the transformation of the vector. Now, the incredible thing is that we can represent any linear transformation with a 2x2 matrix. The transformation L of v can always be written as a 2x2 matrix A times the vector v. This means we can use matrices to perform geometric operations, like reflections, rotations, and scaling. It's a bridge between algebra and geometry. So, how do we find this mysterious matrix A? This is where our second piece of essential knowledge comes in. The mapping of unit vectors gives us all the information we need. Let's define our standard unit vectors. We have I hat, which is the vector 1, 0, and j hat, which is the vector 0, 1. You can visualize I hat as pointing along the positive x-axis and j hat as pointing along the positive y-axis. Any vector in the plane can be written as a linear combination of these two unit vectors. For example, a vector v with components x and y is just x times I hat plus y times j hat. Now, let's see what happens when our transformation L acts on an arbitrary vector v. L of v is L of x times I hat plus y times j hat. Because the transformation is linear, we can pull out the scalars and separate the sum. This gives us x times L of I hat plus y times L of j hat. This is a key insight. The transformation of any vector v is completely determined by knowing only the transformation of the two unit vectors, I hat and j hat. This means that if we know where I hat and j hat land, we know where every vector lands. Let's put this into practice to find the matrix A. Our objective here is to apply this knowledge to find the matrix for a simple transformation. We will use the unit vectors to determine a transformation matrix. Remember, we can write L of v as matrix A times v. So, L of I hat is A times I hat, and L of j hat is A times j hat. Let's write this out. A times I hat gives us the first column of A, and A times j hat gives us the second column of A. This is a profound discovery. The matrix of the transformation, A, is simply the matrix whose columns are the transformed unit vectors. The matrix A is just L of I hat and L of j hat placed side by side as columns. Let's try an example. What if our linear transformation L is a projection onto the x-axis? A vector, xy, becomes x0. First, we find where the unit vectors land. L of I hat, L of psion is still. I hat is already on the x-axis, so it's unchanged. Next, L of j hat. L of L is j hat, which points up, gets projected straight down onto the origin. Now we form our matrix A by putting these two results as columns. A is the matrix, 1, 0, 0, 0. Let's check this. If we multiply our original vector xy by this matrix, we get xer. It works. We have found the matrix that represents the projection onto the x-axis. Our next learning objective is to understand how matrices can perform rotation. You will be able to associate a specific rotation matrix with a geometric rotation. This will allow us to rotate any vector by multiplying it by a special rotation matrix. Consider a linear transformation that rotates every vector in angle theta counterclockwise about the origin. The matrix associated with this transformation is given by cos sine theta, cos theta. Let's see why this is true. We'll use the same method as before and see where I hat and j hat land. If we take the vector I hat, which is 1, 0, and rotate it counterclockwise by an angle theta, its new coordinates are cotheta, sine and cosine. This is just the definition of sine and cosine on the unit circle. Now, let's rotate j hat, which is 0, 1. Rotating it counterclockwise by theta moves it to the point with coordinates. Now, we assemble our matrix using these two transformed vectors as columns. Placing GAM as the first column and CSS, cos theta, as the second column gives us our rotation matrix, R theta. Let's find the matrix for a 90-degree rotation. Since 90 degrees is pi 2 radians, our angle theta is pi 2. We know that cos 2 is 0 and sine pa 2 is 1. Plugging these into our formula, we get the matrix 0, minus 1, 1, 0. Let's verify this. Let's rotate the vector by multiplying it by our matrix. The product is the vector minus 3, 2. If you plot and, you'll see it is indeed a 90-degree counterclockwise rotation. This confirms that our rotation matrix works. We've seen how matrices can transform vectors, but what happens to an entire region, like a square or a circle? Our next objective is to understand how a transformation matrix changes the area of a region. We'll see that the determinant of the matrix provides the answer. The absolute value of the determinant of a 2x2 transformation matrix gives the magnitude of the dilation of regions in the plane. In other words, it's the area scale factor. First, let's remember how to calculate the determinant of a 2x2 matrix. For a matrix A, B, C, D, the determinant is A times D minus C times B. We often write it with vertical bars. Now for the connection to area. Let's start with the unit square, which has an area of 1. The unit square is formed by the vectors I hat and j hat. Its area is 1 times 1, which is 1. When we apply the transformation matrix A, the unit vectors I hat and j hat transform into two new vectors, L of I hat and L of j hat. These two new vectors, which are the columns of the matrix A, form a parallelogram. The area of this parallelogram is exactly the absolute value of the determinant of A. Since this parallelogram came from a square with area 1, the absolute value of the determinant of A is the factor by which the area has been scaled. So, if the area of the original shape is area initial, the area of the transformed shape will be area initial times the absolute value of the determinant of A. Let's revisit our projection matrix 1, 0, 0, 0. The determinant is 1 times 0 minus 0 times 0, which is 0. A 0 determinant means the area is scaled by a factor of 0. This makes perfect sense because projecting a 2D shape onto the x-axis collapses it into a 1D line segment, which has no area. Now for the rotation matrix. Its determinant is cos squared plus sine squared, which is 1. An absolute value of 1 means the area does not change. This is exactly what we expect for a rotation. Rotating a shape changes its position, but not its size or area. The determinant of 1 confirms this. Now let's explore compositions. Our objective here is to determine the composition of two linear transformations by finding their product matrix. We will learn how to combine two transformations into one. The composition of two linear transformations is itself a linear transformation. For example, if we reflect a shape and then rotate the result, the total effect is still a linear transformation. This means there must be a single matrix that performs the combined action of both transformations. How do we find it? The matrix associated with the composition of two linear transformations is the product of their matrices. Let's say we have two transformations, L1 and L2, represented by matrices A and B respectively. L1 maps V to AV, and L2 maps V to BV. The composition, L2 after L1, means we first apply L1 and then L2 to the result. We write this as L2, L1V. Notice the order. The transformation applied first is on the inside next to the vector. Let's see what happens. We replace L1V with AVI. Then we apply L2 to AVI, which gives us B times AVI. Now, thanks to the associative property of matrix multiplication, we can write this as B times A times V. This is crucial. The matrix for the composition L2 after L1 is the product BA. The order matters. Multiplying B by A is generally not the same as multiplying A by B. The rule is, for the composition T2 after T1, the matrix is M2 times M1. Work from right to left, just like reading a function composition. Let's work through an example of composition. Our goal is to compose two transformations, a 90-degree rotation and a reflection over the y-axis, and find the resulting matrix. We will compose a rotation and a reflection. First, let's find the matrices for the individual transformations. We've already found the matrix for a 90-degree rotation. The matrix for a 90-degree rotation, which we'll call R, is 0, -1, 1, 0. Now let's find the matrix for a reflection over the y-axis. We'll call this transformation F. A reflection over the y-axis takes a vector xy and transforms it into -xy. Let's find its matrix, B. F of I hat, which is f of 1, 0, is -1, 0. F of j hat, which is f of 0, 1, is 0, 1. So the reflection matrix B is -1, 0, 1. Now, let's say we want to apply the rotation first, and then the reflection. The composition is F after R. The matrix for this composition is B times A. We multiply the matrices. First row times first column is 0, first row times second column is 1, second row times first column is 1, second row times second column is 0. So, C is 0, 1, 1, 0. This matrix 0, 1, 1, 0 is the matrix for a reflection over the line y equals x. So, we've discovered that rotating by 90 degrees and then reflecting over the y-axis has the same effect as a single reflection over the line y equals x. As a challenge, take a moment to calculate A times B, the matrix for the other composition, R after F, and see if it's different. It will be. Our final topic is inverses. The learning objective is to determine the inverse of a linear transformation, and we'll do this by finding the inverse of its associated matrix. Inverses allow us to undo a transformation. Two linear transformations are inverses if their composition maps any vector to itself. That is, if you do one transformation and then the other, the vector ends up right where it started. The composition gives the identity transformation. The identity transformation is represented by the identity matrix, I equals 1, 0, 0, 1. Multiplying any vector by I leaves it unchanged. It's the matrix equivalent of multiplying by 1. This leads us to our second essential knowledge point. If a transformation is given by AA, then its inverse transformation is given by A inverse times V, where A inverse is the inverse of the matrix A. So, to find the inverse transformation, we just need to find the inverse of the matrix. For a 2x2 matrix A, there's a simple formula, provided the determinant is not 0. The inverse of A is 1 over the determinant of A, times the matrix you get by swapping the main diagonal elements, A and D, and negating the off-diagonal elements, B and C. Remember, this only works if the determinant is not 0. If the determinant is 0, the transformation is not reversible, and no inverse matrix exists. Let's apply the inverse formula. Our objective is to find the inverse matrix for a reflection over the line y equals sine x. This will show how to use the inverse formula. First, we need the matrix for this transformation. A reflection over the line y equals sine x swaps the x and y coordinates. So the vector xy becomes x. Let's call this transformation R. R of xy equals, to find the matrix, we see where the unit vectors land. R of 0 is 1. R of O is 1. So the matrix, let's call it A, is 0, 1, 1, 0. This is one of our most important basic matrices. Now we need to find the inverse matrix, A inverse. First, we calculate the determinant. The determinant of A is 0 times 0 minus 1 times 1, which is minus 1. Since the determinant is not 0, the inverse exists. Now we use the formula. A inverse is 1 over the determinant, minus 1, times the adjusted matrix. We swap the 0s and negate the 1s. Multiplying by minus 1, we find that the inverse matrix is 0, 1, 1, 0. It's the same matrix we started with, This makes perfect sense geometrically. If you reflect a shape over the line y equals sine x, to undo it, you just reflect it over the line y equals sine x again. Reflecting twice is the same as doing nothing. This example highlights the deep connection between matrix algebra and geometry. The algebraic inverse corresponds exactly to the geometric concept of reversing a transformation. Let's quickly recap what we've learned today. We've seen how matrices provide a powerful tool for representing and manipulating 2D geometry. First, we learned that any linear transformation can be represented by a 2x2 matrix. The columns of this matrix are simply the transformed unit vectors I hat and j hat. Second, we discovered that the determinant of a matrix tells us how much the transformation scales area. An absolute value of 1 means the area is preserved, while a value of 0 means the shape collapses into a line or a point. Third, we saw how matrix multiplication represents the composition of transformations. For a composition T2 after T1, the matrix is M2 times M1. Remember, the order is crucial. And finally, we learned how matrix inversion allows us to find the transformation that undoes an original one. The inverse matrix A inverse is the matrix for the inverse transformation L inverse. You are now able to determine the matrix associated with a linear transformation, understand the role of the determinant, find the matrix for a rotation, compose transformations, and determine the inverse of a transformation. This is a foundational topic that you will see in many areas of mathematics and science. Thank you for watching.